Hello. Hello, guys. Hello. Good afternoon. I'm not going to accept any more submissions, all right? It's already 3 o'clock, so I have to be strict because, I mean, in the last few weeks, people have submitted late, and I gave them full, I still marked them, but this week I'm not going to accept any late submissions, right? So if you haven't handed in, then you will get 0 mark, okay? All right, guys, so now, so on Thursday last week, we talked about sampling distributions. Now what I like to do now, on Thursday last week, briefly, so sampling, this is stuff we did, you don't need to write this down. The sampling distributions are distributions that arise through functions of data, right? And in this course, I shall talk about 2 sampling distributions. The first one is known as the chi-squared. The first one is known as the chi-squared distribution, and the second one is known as the student's t distribution. Okay, and so on Thursday last week, I talked about the chi-squared distribution, which is given by this formula here. So a chi-squared distribution has this as the density function, and it has a parameter a, which is referred to as the degree of freedom parameter. It is defined on the positive real line, and the parameter a is also positive. And this is the notation I use for a chi-squared random variable. And over here, this function here is known as the gamma function, right? In R, I know you're trying to learn R, okay? In R, the commands for computing the density of a chi-squared is this one, and the command for computing the CDF of the chi-squared is this one, right? And then I also talked about briefly the gamma function. The gamma function is defined by this integral, is defined as the integral of this function, and is defined over the entire real line except at the point 0, -1, -2, etc. And these are some properties of the gamma function. Okay, and then I talked about some properties of the chi-squared variable. So this is the first property, which says that a function of the data, namely this one here, which involves only the data itself, has a chi-squared distribution with n-1 degree of freedom. The expectation and the variance are a and 2a. The square of a standard normal variable is chi-squared with 1 degree of freedom. And if you have 2 independent chi-squared variables, then their sum is also chi-squared variable. Yeah? And here are 2 more properties I talked about on Thursday last week. Yeah? And then I proved one of the properties, namely property number 7. And this proof is kind of the quiz number 4, which is due next Monday, is kind of similar to this. Well, it's a little bit more advanced than this. So if you can understand this proof, you should be able to do quiz number 4, right? So this here, I proved the result that I proved number 7, which is that the sum of the deviations can be decomposed like the difference of these two terms, right? So if you follow what I've done here, you should be able to do quiz 4 easily. All right? And this is the end of the proof. And then I also proved, property number 2, guys, where I showed that the expected value, the expected value of a chi-squared variable is equal to A. All right, is equal to A, right? Now, what I like to do today is maybe do an example. Before I do an example, let me also prove number 3, right? The proof of property 3 is, the property 3 says that the variance of a chi-squared variable is 2 times A, right? So if right, we can write the variance and this is the expectation of x squared minus a squared, right? So in order to derive the variance, we need to derive the expectation of the square of x, right? So that's going to be the expectation of x squared is the integral from 0 to infinity of x squared right? This is the integral, right? This is the density of the chi-squared. You're multiplying by x squared, right? Now, to do the integration, you can do a substitution. So I'm going to make the following sub. So let's say y equal to x by 2, which implies that x equal to 2y, which implies that dx is equal to 2 dy. Right? Now, if you make the substitution, this will become 0 to infinity. X will become 4y squared. Are you with me, guys? Let me know if I make any silly mistakes. All right, so this will become the 2 and the 2 will cancel, so it's going to be 2 Okay, this is what you get. Okay, correct me if I make any mistakes, right? I mean, I'm known to make a lot of mistakes. All right, so this will be 4. Now, can you tell me what this integral is from what we learned last week? What is this integral equal to? Equal to the gamma function at a over 2 plus 2. Do you follow why? It's just because of the definition of the gamma function. Remember, the gamma at alpha is the integral of t power alpha minus 1. So whatever the power here is, you add a number to that. So you add a number to 1 to this, it becomes a over 2 plus 2, right? Then using one of the properties I mentioned last week, that this you can write as all right, this is using the property that gamma at x plus 1 is x times gamma at x. I'm using this property here, right? And using this property one more time, right? All right. This is using once again the same property. You get this to this, right? And these two guys cancel out, right? So what you get is a plus 2 times a, which is a squared plus 2a, right? So we have shown that the expectation of x power 2 is a squared plus 2a. Now going back over here, which the variance is the difference between these two. So hence the variance of a chi-squared variable is the difference between a squared plus 2a and a squared, which is 2a. So we have proved property 3 that, are you guys with me? We have proved the property that the variance of a chi-squared variable with a degrees of freedom is 2 times a. It's just the difference between these two, which is this, the difference between a squared plus 2a and a squared, which is 2a, right? All right, now the next one, I'm going to do an example. I haven't done any examples on the chi-square distribution, so this is example 1. Right, so we have a random sample from a normal distribution with mean 1 and variance 1. We want to find the probability s squared. Remember, s squared is a sample variance. A couple of weeks ago, I gave a formula which was not correct, but I think I corrected that online. I corrected the formula for s squared online. So So once again, I will repeat that the corrected version. Issue S squared denotes the sample variance. S squared denotes the sample variance and is defined to be 1 over n minus 1. Is not what I had written it as 1 over n, which is not correct. So the correct divider is 1 over n minus 1, but I corrected this online, if you see in the notes online. And the S is the sample standard deviation. So this is known as the sample variance, and S is the square root. So this is the sample. This is the sample variance, this one, and this one is the sample SD, right? Okay, correct. So if you have written it incorrectly, please make sure that you do correct it. But I have corrected it already online in the scan notes. I have already corrected it. So all right. So returning to the question, we want to find the probability that S squared is greater than 3, okay? Which is the same as saying that all right, we want to find the probability that this is greater than 3. Yes? All right, so this becomes the probability that are you guys okay? Yes? Okay. Now, do you guys remember this? If you look at the properties, of the chi-square distribution I talked about on Tuesday, let me get it to you now. Do you remember this property that if you have a random sample from a normal distribution, then this guy here should have a chi-square distribution with n minus 1 degree of freedom, right? So what distribution will this have? Huh? Come on, guys. What distribution will this have? Chi-squared with yes? All right, by property number 1 of the chi-square distribution, right? This guy here will have a chi-square distribution with 9 degree of freedom, or a equal to 9, right? Okay. So you can write this as 1 minus the probability that a chi-squared variable with 9 degree of freedom is less than or equal to 27, or you can write it as 1 minus f. I'll just explain in a minute what f means, but 27, and here this guy here denotes the CDF of a chi-squared variable with 9 degree of freedom. All right. So that's the answer to the example 1, right? So you can, I mean, if you have tables for the chi-square distribution, I mean, in the exam you will get tables. You may be able to read it from the tables for the chi-square distribution, right? But I'm not going to do that now, just because of time issues, right? Any questions so far, guys? Yeah? Yes? Okay. All right. Next one. So far we talked about only one of the two sampling distributions. The next one, number 2, number 2 is known as the student's T distribution, right? By the way, the student's T distribution is not in the printed notes, all right? So it's only it's on top of, it's not in the printed notes. So please make sure that you read it from the scan notes, right? This is the PDF of the student's T distribution, and is defined from -2 to plus infinity. And A is once again, sorry, this is A. A is a positive parameter, and once again it is referred to as the degree of freedom parameter. Right? Okay, and the notation I shall use to denote a student's T random variable, I will write x tilde T with degree of freedom A. So this is the notation. This is the notation I shall use to denote a variable that has a student T distribution, right? Now, there is a story behind the student T distribution. The student's T distribution is due to a famous statistician called William Gossett, and the reason that the name, instead of having his own name, it is called a student's T distribution is because of this. Because he was a statistician for a famous Irish beer company. I mean, those of you who drink beer, you probably guess what the name of the company is. You know Guinness, right? The Irish beer company Guinness. So he worked for that company, and one of the policies of the company is that you're not allowed to disclose any research, right, under your own name. So he decided to call his distribution student's distribution, right? Because it's because of the disclosure principles, right? So that's how it took the name student's T distribution. Instead of calling it Gossett distribution, they call it student's T because of the disclosure principles of the company, right? Okay. All right, guys. the R command okay. In R, the commands for computing the PDF and the CDF of a student's T distribution are dt. Then I hope you can read my writing. dt is for density of T. pt is for the CDF of T with degree of freedom equal to df stands for degree of freedom equal to A, right? All right, guys. The next one, some properties. The first property, right? If a random variable x has a t distribution with a degree of freedom, then number one, the expectation of x is equal to 0. Number two, the variance of x is equal to a divided by a minus 2, right? Right. Number three, as a approaches infinity, right, t of a approaches as a approaches infinity, t of a approaches a standard normal variable with mean 0 and variance 1. Right. The property number 3 is hard. It's not easy to prove, but the first two properties are pretty. They should not be difficult to prove. I mean, you should be able to prove 1 and 2, but for number 3, the proof is not easy. But if you look at the course website, if you look at the course web, all of you know where the course website is. The proof of number 3 is given at a link at the course website, right? Okay. I will try to prove one of the first property 1 or property 2 later on. Okay. All right. Next one. Now, if you look at the student's T distribution, the PDF, this is the PDF. This is the PDF of the student's T distribution. Now, there is no mean parameter. Remember, for the normal distribution, there is a mean parameter and a scale parameter. But this one has neither of the two parameters. It doesn't have a mean parameter and it doesn't have a scale parameter. So you can actually make this density. You can actually make this density to have a mean parameter and a scale parameter. And this is how you do it, right? All right? So as I gave it to you a minute ago, the version I gave you has no mean parameter, has no scale parameter. Now, I'm going to give you a new version. Okay, I'm going to give you a new version which has a mean parameter and has a scale parameter. So it's as follows. Come on, guys, keep quiet, guys. All right? You see what I've done. I have added two more parameters. Mu is the mean parameter, sigma is the scale parameter. So now it has three parameters. X from minus to plus infinity. Mu is the mean parameter, right? It's the mean. Is the mean parameter, and sigma is a scale parameter, and A is, as before, is the degree of freedom. All right. So this density here is an extension of the standard student's T density in order to have a mean parameter and a scale parameter, right? Right, and I shall use the following notation that if a random variable x has this density, then I shall use this notation. All right, this is the notation meaning that a variable x has this PDF, right? Okay? Right, next one. All right, before I go to the next one, let me, just a minute. All right, in R, yes. R commands, yes. Now, I gave you R commands for computing the standard student's T density. Now I'm going to give you R commands for computing the extension, right, which has three parameters, right? Okay, they are as follows. Now, before I write down anything, let me ask you. Now, do you guys know how to download packages in R? No? Packages. Like, R has several packages, contributed packages. Do you know how to download them? No? All right. I know you say no for everything, I know. I can, all right. Now, let me give you, okay, just an aside. Suppose there's in R has hundreds of packages. Like, there's something called the base package, which is what you normally use. And there are so many, I mean, if you go to the website of R, you will see there are hundreds of packages doing specific things for a distribution that you probably never heard of, right? Okay, so now, suppose you have a package called, say, ABC, right? Suppose, I mean, I'm just making up this name, all right? Suppose there's a package, R package called ABC, right? And you want to install the package in your R, all right? And the commands for doing that are as follows. Right, this will be one command, and then right, so these two commands, right, will install a package by the name ABC. I mean, just making up the name ABC, but it could be any name, right? It could be any name of a package, right? So if you issue these two commands on the prompt for R, you will have the package ABC installed in your environment, right? Okay. Now, all right. Returning to the R commands for the extension, the commands are as follows. The commands for the extension are as follows. The first one is dt scaled x df equal to a, mean equal to mu, and st equal to sigma. All right, this will compute this command all in one line, okay? Will compute the PDF that I just gave you, which is this one here, right? And the following command, pt scaled, so you replace d by p, pt scaled x, df equal to a, mean equal to mu, st equal to sigma, will compute the CDF. Right, we'll compute the CDF. So maybe I should say CDF of x t mu sigma a, right? Of x right? Are you guys okay? So, any questions so far? There's no need to copy this down, guys. I will scan this as soon as I return to my room. I will scan it and post online, right? So this is the command for computing the PDF of the extension, and this is the command for computing the CDF of the extension, right? Now, by the way, I like to remind you at this point. about the R coursework. Remember R coursework I gave you at the first day of the classes? You already forgotten or what? The R coursework is worth 10% of your total mark, and it's due on the 29th of April, which is Monday, by 3 p.m. right? So make sure, I know you have plenty of time, but please hand in the work to me in person. If I'm not in, you can put it under the door. It shouldn't be more than 5 pages long, 5 printed pages, right? And I will try to mark it as soon as possible, possibly not on the same day, because marking, 5 pages will take me a long time. I can't possibly do that on the same day. Shh. But I will try to return it to you as soon as possible, right? Okay? All right, guys. Now, next one. Shh. Can you keep quiet, guys? You're not going to stay here forever, man. You're not going to stay here forever. Right. The next one are properties. Sorry, guys. All right, these are the two properties of the extension, right? Remember, this is the notation for the extension of the t-distribution. Now, one thing I forgot to mention before it is too late. Oh, yeah. This here we are. All right, one thing I forgot to mention is the following. There is a property number 4 for the standard t distribution. There is a property number 4 I forgot to mention. Right? If you have a random sample from a normal distribution with these parameters, then you have x bar minus mu divided by s by root of n has a t distribution with n minus 1 degree of freedom. Right? Right, this is an important property. Again, once again, I don't expect you to know how to prove this, but if you can prove it, that's great. Right? So S here is the sample standard deviation. S is the where S is the square root 1 over n minus 1 all right. Okay, that's the sample standard deviation, right? So these are there are 4 properties for the standard t distribution and 2 properties for the extended t distribution, right, which I just gave. This is the extended t distribution, right? Now before you leave, shh, why are you guys in a hurry to leave, guys? Okay. Now, before you leave, I would like to do an example because I haven't done any example for today. All right. All right, guys, listen to this example. You have U has a normal distribution with parameters 3 and 16, and you have V has a chi-square distribution with parameter 9, right? And you are told that U and V are independent random variables, right? The question is to find the probability that U minus 3 is less than 4.33 times the square root of V, right? Now, how would you do this? So we want to find the probability of U minus 3 right, which is equal to the probability that n, remember U is a normal variable with parameters 3 and 16, minus 3 is less than 4.33 root of V. Now, if you take away 3 from this, what would you get? You will get a normal variable with 0 mean and variance 16. Okay, this is V, guys, V. Right, now this you can write as 4 okay, right, and this you can write as follows: normal yes, you with me, right? And one more thing, I'm gonna right, okay, you with me, guys, or no? Yeah. And according to the property that I just gave you, which a minute ago, let me show you where it is. Where's the property that I just mentioned? Yeah. According to the property that I just mentioned, right, this guy here has a t distribution with 9 degrees of freedom. And you can, if you have a table for the t distribution, you can read this. So that's the answer. So the answer is the probability that a t variable with 9 degrees of freedom is less than this number, right? Do you see why this is equal to this? It's because of this property here that I just mentioned, right? Yeah. Yeah. Yes. Why? What?
Sorry. We used this property, right?
Yeah.
Yeah. And the square root not n, and then that's that's t to the n minus one. I thought that's. But if we divide it.
No. Sorry. I used another property. Sorry. I will write it down here. Sorry. I will write it down. So you're. Hello. Which quiz did you do?
Sorry?
Which quiz is that?
Quiz.
Chi-squared A.
Divided by a.
Yeah, this is
Okay.
this is a property I used.
Okay, sure.
This is different from the one I mentioned.
Okay.
Okay.
Okay. Thank you.
I said, sir, quiz 3.
Which is up today?
You're late, sir. You're already. I said it's 3 o'clock.
Oh, okay.
It's okay. It's okay. I will take. Don't be late next time. Okay.
All right.
Okay.
Okay.
All right. See you, man.
Why is T9 here? There. It should be T8, right?
Huh?
This one, the last step. Should it be 8? Because
No. I used this property, sir. This is a different property, not the same as this one. This is a well-known property too. I didn't mention that in the list of 4 properties. It's not there. Yes. But you're late. I said it's 3 o'clock. Not. It's already 4 o'clock now. Yes. But please don't be late. Anyway, you can copy. Yes,
Can I
ma'am.
ask you a question?
Yes.
How would you distinguish between this part and that we did the other one?
Which
the
one?
Sort of,
That's the central limit theorem, sir.
Uh-huh.
Here, this is sample standard deviation. This is population standard deviation.
Okay, and that's the sample.
This is a sample one.
Okay.
They're two different.
Sir, the coursework should be printed, not online.
Yeah, it should be
Only
printed. Yeah, it should be
Okay.
printed. Yeah.
29, that's the beginning of the end of the vacation?
Yeah.
Okay, 3 o'clock or?
3 o'clock. Yeah.
thank you.
3 o'clock. Yeah. It should be this one. Sorry. It should be this property I have used.
we were just going to say,
Yeah.
You times that by 3, but you divided that by 3. I'm confused.
So it's 3 times 4 is 12. Yeah. I divided by 3. So you divide here by 3 too. So you get 12.
No, you divided by 30.
You times
You divided by 30.
Sorry. Yeah, I divided by 9, so I have to multiply by 9. So square root of 9 is, yeah, square root of 9 is 3, right?
Yeah.
So if you bring square root of 9 here, it will be 3. So 3 times 4 is 12.
But you've divided there and times there.
Yeah, I know, but I know what you're saying, man. But look, if you divide by 9, you have to multiply by 9 here. You follow, right? So, which is the same as saying divide by